lens. In the previous lecture, we studied about human eye. We saw all the components of human eye and especially lens. We also got to know the function of each and every part of the human eye. Now, we all wish for a good eyesight, but unfortunately, some people have defects in their eyes, which we often refer to as poor eyesight. Well, now we are going to discuss few of the defects and their correction. So the first one is myopia. That means nearsightedness. So nearsightedness means a person is able to see nearby objects properly, but finds difficulty in seeing distant objects. So person's near eyesight is good, but far eyesight is not good. So now, as we discussed before, there are 2 points for a good eye, that our lens, which does the whole task, that the role of lens is to focus the image onto the retina. If lens is able to focus the image properly on retina, then we say that our lens is working properly and we have a good eyesight. And ciliary muscles are there, which I haven't depicted here, but ciliary muscles, we talked about those muscles and they perform a very crucial function. They hold the lens and they relax or contract the lens depending on the situation. For example, if we have to see distant objects, then it relaxes, the muscles relax and our lens becomes thinner so that the focal length increases. And if focal length increases, then we are able to focus the light rays coming from a distant object properly onto the retina. And when we have to see nearby objects, in that case, ciliary muscles contract and our lens becomes thicker. Due to that, the focal length decreases and then we are able to see the image of a nearby object because the light rays are coming from very nearby object, and that's why focal length needs to be shorter. Power of accommodation means how distinctly our eyes can produce image of any object. So power of accommodation is basically how efficient our ciliary muscles are, how efficient our eye lens, which is a convex lens, is in forming the image onto the retina. For distant objects, there is no limit. We can see up to infinity. But for nearby objects, it's 25 centimeter. That is the distance for the nearby object at which our eyes can produce its image clearly and distinctly. If we bring the object closer than that, then image gets blurred. So that means the far point for a normal eye is infinity. We can see as far as we can. So the defect we are going to study is myopia, that means nearsightedness. Person is able to see nearby objects very much clearly but has difficulty in seeing distant objects. So sometimes students face difficulty in seeing the blackboard. If they sit at the back benches, then they find difficulty in seeing the text written on the blackboard. So in that case, they are said to have a myopic eye. That means they are able to see nearby objects properly, but they have problem in seeing distant objects, and then they are made to sit onto the front desks. So let's see what happens. So here in A, we are discussing that what happens to the far point of a myopic eye. So this that I have drawn, the diagram, this is a diagram depicting far point of a myopic eye. Now the far point of a myopic eye is not infinity. That means the person cannot see distances which are quite far away, infinite distances. the person is not able to see. So its far point decreases. So now here we have shown that light rays are coming from a point O, which is definitely not infinity. So far point of a myopic eye is basically less than infinity. So at a particular distance, which is obviously greater than 25 centimeter, a distance greater than 25 centimeter but less than infinity. Thus, the person is able to see the objects which are at 25 centimeter very much easily, and also person is able to see objects which are placed at distances greater than 25 centimeter. But person has difficulty in seeing the objects which are placed at infinity, like very far away objects. So the far point of a myopic eye is obviously greater than 25 centimeter but less than infinity. So if I say that this point O is a far point of a myopic eye, then this lies between 25 centimeter and infinity. It is somewhere in between. So due to that, if the object is placed at this point, far point, then person is able to see that object clearly, because you can see that light rays are coming from this object and we have not shown parallel rays. Now you should know why have we not shown the parallel rays, because point O is not at infinity. Only the light rays which are coming from infinity, we show them to be parallel. So here point O is at some far distance, but it is definitely not the infinity. It is some particular distance, obviously greater than 25 centimeter. So from here we say that the rays are spreading out and then they are entering the eye. Now whenever we discuss the defects, we just draw eyeball, the cornea part and the lens, because all we have to show is lens doing the role and forming the image on the retina. So now a convex lens, which does the task of converging the light rays, it will converge those light rays onto the retina. This point is retina. And for a human to see objects properly, to see their images properly, image should form at retina only. Retina is the only spot where an image should form. If image forms at any other point inside the eyeball, like if it forms anywhere else, if all the rays converge on any other place, then person would not be able to see the image, because this portion will not send any signals to the brain. Only the retina has those receptors which are directly connected to the brain via optic nerve. So this is very much important. But here, this far point is some fixed distance which is less than infinity. So basically the person can see objects clearly up to some far distance, but which is not that far, which is not infinite. So if objects are brought up to that distance, then person has no problem in seeing the objects. But then what actually happens if light is coming from rays which are at infinity? So how does a myopic eye behave? That when light rays come from infinity, then this eye faces problem. What happens? That light rays are coming, and now we have shown parallel rays because they are coming from infinity. So now obviously convex lens will converge the light rays, but they converge the light rays at this particular point. So image is forming in front of retina and not on the retina. But to see properly, image should form at the retina, which is not happening here, and thus the person would face difficulty. He would find it difficult to focus. He would try to shrink his eyes, You must have seen if people have to read something from far off distance and they have kind of myopic eye, then they try to contract their eyes so that they can see it properly. Why? Because image is forming in front of the retina and not on the retina. So they are getting some blurred visions. So this is the problem. If object is taken from infinity to a particular point which is far point of myopic eye, then things get normal. Then the person is able to see the image properly, because then the rays would be converging at retina. But if the object is placed at infinity and light rays are coming parallel, then there is a problem. And what is the reason for that? Now, what is the reason of this defect? So, first reason is excessive curvature of eye lens, and second possible reason is elongation of the eyeball. Now, in normal eye, when eye sees a distant object, then ciliary muscles relax and our lens becomes thin. When lens becomes thin, then its focal length increases. This focal length increases, and due to that, lens is able to form the image of that distant object onto the retina. And when we see nearby objects, in that case, our lens becomes thicker. It becomes thicker, widen. In that case, its focal length decreases. So when we are holding a nearby object, when we are holding an object which is near to our eye, then rays don't need much distance to travel. So in that case, we need focal length of the lens to decrease. So if lens is thinner, then its focal length increases and it will converge rays at larger distances. But if lens gets thicker, then its focal length decreases because it has lot of tasks to do. That's why it has widened up. So when it becomes thicker, then it will try to focus to converge all the rays at a shorter distance. So this is the role played by lens. If it gets thinner, then its focal length increases and it is capable of converging light rays at larger distance coming from a distant object. But when lens gets thicker, then its focal length decreases and it focuses the light rays at much shorter distance. So if curvature of eye lens increases, that means if lens gets thicker, then we know that its focal length will decrease and it will try to converge the rays at much shorter distances. So this could be the possible reason. Excessive curvature of eye lens means this curvature that we are talking of, it has widened, it has got thicker. This is the meaning of this particular statement. So if this happens, then we know that if lens gets thicker, that means if its curvature increases, then its focal length decreases. So focal length is basically, it is the distance between this lens and the retina for a normal eye, because a normal eye should always focus all the rays onto the retina. That is the focal length for a normal eye. But here its focal length is decreasing and that's why it is converging all the light rays in front of the retina. So one possible reason is this. Other possible reason can be elongation of the eyeball. So if our lens is working properly but our eyeball increases in length, if it elongates, then also what happens, that light rays would have to travel much larger distances. So the lens would be converging them in its normal behavior, but basically our retina would shift due to elongation of the eyeball. So there are two possible reasons. First, if there is some defect in the lens itself. that if lens gets thicker or its curvature increases, then its focal length decreases and it will converge the light rays at much shorter distance. So image will form in front of the retina. Or the other case could be elongation of the eyeball, because if eyeball elongates, then also if lens is working properly, it will try to converge the rays at its normal focal length, but retina would too have shifted due to elongation, and then also again image will not form on the retina. So now what should we do to correct this defect? Now we can use concave lens here. Now we all know what is the use of concave lens, what is the role of concave lens. They are the diverging lenses. They diverge the light rays rather than converging. And our eye possesses a convex lens already, which does the task of converging rays. But what is the problem we are facing here? That it is converging rays at much shorter distances. We don't want that. So ideally what should happen? If we are able to somehow diverge these light rays coming, see here we are getting parallel rays, and we know that the role of our eye lens is to converge the rays, but it is converging at much shorter distances. So if we diverge the incoming rays, then what would be the case? That convex lens would again try to converge them, but then using this particular lens of proper power, by using all the calculations and measured quantities, we can make the light rays fall onto the retina again. So here what is happening? Light rays are coming parallel, that means they are coming from infinity, and we have placed a concave lens in front of the light rays. Concave lens would diverge. So basically these rays are diverging. It would diverge the light rays, and now our eye lens would face diverging rays. It will again try to converge those rays, but now it takes more power, and that's why it will try to converge them onto the retina. If we had used convex lens here, then we would have degraded the whole situation, because convex lens would produce further converging rays, and if those converging rays fall upon our convex lens, then it would produce image at even shorter distances, which we don't want. We want to increase the focal length. We want to increase the focus where rays are going to fall. That is the point retina. So concave lens would diverge the rays, and those diverging rays will fall upon the convex lens, and then they would try to converge them again, but then definitely the rays would fall onto the retina. So for that, this is the reason that doctor prescribes you a particular power of the lenses. Every person has some particular degree of defect, and that's why a particular power of lens is prescribed by the doctor. So they first check by giving you different lenses. They just see what kind of problem you are having. They often encourage you to read a few letters on a chart, mostly pasted on a wall, and then they say that where is actually your focal length of the eye is falling, or where the light rays are actually falling in case of your eye. And then by noting that focal length and using the lens formula, they decide that which power lens would be good for you. In fact, for calculating the power of lens, we only need focal length. So in reality, the doctors, they see the object distance because they have pasted the chart at a particular distance. So they know you, and they also know the V, because they will give you different lenses to see the letters written on the wall. So whenever you get a particular proper image of that letter, they just measure those distances, and using those measurements they find the exact value for the focal length and as well the power of lens. So then they prescribe you a particular concave lens of a particular power. So this was all about eye defect myopia, which is also known as nearsightedness. We studied that what is the problem, that normal eye has far point infinity, but for myopic eye far point decreases to some distance which is less than infinity but greater than 25 centimeter. And what is the problem which myopic eye faces? That image forms in front of the retina, and what are the possible reasons? After that, how can we correct it? We can correct it using concave lens. So we'll continue studying the other eye effects in our upcoming lectures. Thank you.